All right, as I said, welcome to Virtually on the Road in Paso Robles. Just a couple of housekeeping items. If you want to ask a question, you can type your question into the chat, or also, since this is a webinar, in the Q&A, and we will ask it for you. We will be recording today's program, and we'll send the link to the registered attendees. Because this is a longer program and not just a 1-hour program, it does take longer to process. So we'll try to send it out this afternoon, but if it's not quite ready, then you'll have it probably first thing Monday morning. Well, we'd like to thank Mark Vatney. He's the Water Management and Biometeorology Advisor for San Luis Obispo County and Santa Barbara counties, for suggesting topics and presenters relevant for this region. I'd like to thank Caroline Bamforth for help with logistics. That includes registration, answering many of your questions along the way. I'd like to thank all of the speakers for their willingness to share their time and expertise with us today. And we'd like to thank, of course, our extension partners, without whom we would not be able to provide these programs. And I just want to give a shout out to our Aggie Gold partners, especially J. Lore Vineyards and Wines, who is from the San Luis Obispo region. So thank you, J. Lore, and also to Constellation, Ian J. Gallo, and of course, American Vineyard Foundation, who gives me a grant each year to help fund some of these programs. So thank you all. All right, so we are going to get started. Our first speaker is Cristina Lezcano. She's an assistant professor of soils and plant nutrition in the Department of Land, Air, and Water Resources here at UC Davis. And her title is, "What Does It Mean to Apply Regenerative Agricultural Practices to Grape Growing?" And I'm going to stop sharing, and we will begin. Thank you, Cristina.
Thank you very much. I'm going to share my screen. Can you all see my full screen?
Yep.
Perfect. All right. So thanks so much for inviting me to be here today. My name is Cristina Lezcano. I'm an associate professor of soil ecology, plant nutrition as well at UC Davis, and I'm going to talk about some work that we have been developing over the last maybe six to 7 years in looking at regenerative management and wine grape growing and benefits and potential trade-offs. And so over the last years, there's been increased awareness and recognition of the important role of farmers and their management practices on not just supporting crop production, but also environmental quality. And grape growers in California, they are faced with several challenges at the moment. Like, for example, having to adapt to extreme weather events and climate whiplash, and having to reduce environmental pollution and mitigating climate change and adjusting to, regulations that are always changing. All of this while maintaining high grape quality that is characteristic of California wine grapes. And so there are several management practices or management approaches that can be used to face these challenges, all of them with different emphases and different priorities and different levels of environmental protection. And so we can see examples in this graph here. Sustainable agriculture that's been around for a long time. This approach, what it's trying to do is improve efficiency of management practices to reduce environmental impacts while maintaining agriculture production. On the other hand, climate smart agriculture, which could actually be enclosed into sustainable ag, it has a strong emphasis on climate change mitigation, adaptation. So it proposes a series of management practices that are very strongly focused on reducing greenhouse gas emissions and improving carbon sequestration. Both these disciplines, sustainable ag, climate smart ag, they both kind of, they're based on scientific principles of agroecology. This is a scientific discipline that has been developing for the last 100 or more years, and it emphasizes self-regulating systems and soil ecology as a way of reducing externalities and, environmental impacts as well. So it's based on ecological principles. So where does regenerative farming fit in all of this picture? Regenerative farming kind of fits at the intersection of all of these different currents or disciplines. It tries to reduce environmental impacts. It's strongly focused on, climate change mitigation and adaptation. And it is very based on scientific principles of agroecology. So we could also think about regenerative farming as a step forward, as like a little bit more than a sustainable farming, in the sense that, for example, compared to the status quo, which would be a more of an extractive approach to agriculture, and compared to sustainable farming that aims to just like cut on environmental impacts, regenerative farming, it goes a step beyond, in the sense that it tries to nurture agroecosystems, not just reduce impacts and preserve environmental quality, but like enhance environmental quality. And this is like the main difference with like previous management approaches. So what exactly then is regenerative? And the thing is that there's no legal definition yet. The CDFA, for example, is currently working on these, asking different experts. It is very strongly based on outcomes. And so, what do we want to get out of the farming practices? And it's very centered on soil health. So this is something that we can see. This was a figure from a study published in 2020, where they looked at everything that has been published so far on regenerative farming, and to kind of extract the main topics and the main farming practices that these studies had. So what this scientific study saw is like 3 or 4 main topics in terms of the main goals of regenerative farming. On one hand, there's a very strong emphasis on economics, so profitability of the farm, improving human health. But the majority of the studies are focused on environmental quality, so reducing environmental externalities, improving ecosystem health, and specifically on soil health. So there's like a very, very strong emphasis on supporting soil health, sequestering carbon, improving soil physical quality, etc. Regenerative farming is therefore based on the principles that support soil health. So adding soil organic matter, minimizing soil disturbance, maximizing crop diversity, keeping the soil covered, maintaining a year-round living root system in the soil, and integrating livestock to improve organic matter and nutrient recycling within agricultural systems. What does this mean for viticulture? There's many different practices that can meet these principles. Like, for example, to increase soil organic matter, we can obviously add compost, but there's other organic amendments that can be used, like vermicompost, liquid compost, biochar, etc. Reducing disturbance is met through reduced till or no-till. Cover cropping, it's a practice that has lots of benefits, meets all of the principles pretty much, improving organic matter, keeping the soil covered, having a living root in the soil, improving diversity. And then sheep grazing is a practice that it's becoming very popular among wine grape growers as a way of integrating livestock into vineyards. Another thing about regenerative farming is that it proposes the stacking of practices. So the combination of practices, one on top of each other, to get the maximum benefits out of them. And so the basis of this is that, for example, applying compost on a vineyard that also it's no-till and it has a cover crop has more benefits to soil health and soil carbon than using the practices alone. So 2 + 2, it would be 7 rather than 4, right? In terms of carbon sequestration. There's many growers that have adopted these principles and these practices already for a long time, and they're very successful. These are 2 examples, but there are many more in California. So Piscine's Ranch in Monterey, Tablas Creek in Paso Robles, they've been doing this for a long time. They're some of the pioneers, early adopters. But more and more we see farmers transition into regenerative farming. And so, for example, we see more and more vineyards that are now regenerative organic certified through the whole state, right? The use of soil health management practices is also very heavily incentivized by federal and state level initiatives. This is through programs that aim to reduce or to mitigate climate change. And so, for example, the USDA had these partnerships for climate smart commodity call a couple of years ago, and they were giving away multi-million awards to agricultural industry and academic institutions to reduce environmental pollution, greenhouse gas emissions, etc. And the state of California offers incentives to growers to adopt these practices every year through their Healthy Soils program. So there's many reasons for farmers to think about regenerative farming at the moment, but there's also lots of questions open in terms of how is this working for wine grape production, whether it allows growers to meet these challenges that we mentioned before of like adapting to climate change, being able to mitigate climate change, and maintaining great quality, right? So is regenerative farming really the path forward for grape growing in California? So we've been working on addressing these questions in my group. And so I'm gonna give you some examples of projects that we have going on or we have completed in the last years. And the first project I want to mention, and it's looking at whether regenerative management can help with climate change adaptation. And so what we've seen in California, it's like a change, a pretty quick change between extreme drought to extreme precipitation events that lead to floods, right? So what we've seen is that to adapt to this climate whiplash and extreme changes in precipitation, we need soils that are able to absorb all of this water when it comes, so quick, infiltrate the water, but also retain it and make it available for the crops, right? So having a healthy soil is essential for these, and soil structure specifically is one of the most important properties that is going to regulate water infiltration, water retention, and water circulation. We have good structure when we have roots growing in the soil, soil biota, fungi, earthworms, etc., that create these aggregates that we can see here in this picture on the left. Aggregates are essential for retaining water, but also promoting aeration of the soil. On the other hand, on the right, we see a compacted soil. This happens when we till, for example, too frequently. We go with the tractor too much on the soil, and we destroy those aggregates. We disrupt them, and we break them down into small particles of silt and clay. And so it creates that crust on the soil. So we wanted to see whether regenerative farming is really helping improve soil physical health and water circulation in vineyards. This is a project that is supported by the USDA. It's a NIFA project that is being led by Dr. Nal Monidal, postdoctoral researcher in my group, and Sarah Brickman, which is a PhD student also working with me. So what they did is they went out to several vineyards in Napa Valley, and they identified pairs of vineyards that were side by side on the same soil, but had different management. So we had on the one hand, a soil health managed vineyard, which had all of these practices: no-till, cover cropping, sheep grazing, the use of compost, for more than 5 years, all of them stacked together. And then on this, just side by side, the neighboring vineyard was a conventional vineyard that didn't have these practices. And so they identified 3 of these paired sites. And they went out last year, they got soil samples, they brought them back to the lab to study soil physical properties. So what they've seen is that, interestingly, soils that receive these soil health or regenerative management practices were more resistant to breakdown from water perturbation than soils that were conventionally managed. So in this graph here on the left of the slide, we can see the 3 pair sites, site 1, site 2, and site 3, with conventional management in red and soil health management in blue. And so what they've seen is that the proportion of water-stable aggregates was consistently higher in those sites that receive soil health management practices than in the sites that receive conventional management practices. So there was higher stability of the aggregates when they were subjected to water stress, which means also lower rates of soil erosion. And so this is what we've seen when we calculated the erodibility factor of these soils. And so for the conventionally managed soil, what we see is that this erodibility factor was also significantly and consistently higher across the 3 paired sites in the conventional managed soil. These differences in erodibility and, like the response to water stress were associated with a different distribution in aggregate sizes in these conventional and regenerative management sites. So what we see in this picture here is the 3 paired sites and the distribution of different aggregate sizes, from large microaggregates all the way to small aggregates or microaggregates and fine particles of sand, silt and clay all the way on the right. So what we've seen, again, consistently across the 3 sites, is that the proportion of large macroaggregates was higher in the soils that were managed through soil health practices or regenerative practices as compared to the conventional soils, whereas the conventional soils had a higher proportion of those fine particles of the sand, the silt, and the clay, and the very small microaggregates. So what's happening here is the management is disrupting the intensive management in the conventional sites is probably disrupting the large microaggregates and breaking them down into the smaller particles, which could lead to, again, higher rates of erosion and also potentially lower rates of water holding capacity. And so that's what we study currently in our lab. We're right now collecting measurements of soil water retention in the soil samples. We don't have the data yet, but we hope to have it very soon. All right, next question. We know that regenerative farming could help adapt to these climate extremes by improving the stability of the soil. Is regenerative farming a valid strategy for climate change mitigation? So for sequestering carbon and reducing greenhouse gas emissions. This is the work of Connie Wong, which is currently a PhD candidate, also working in my lab. And she did for her master's thesis a study at one of the vineyards of J. Lohr in Paso, Robles. And what she did is applying increasing rates of compost, 0, 2, 4, and 6 tons per acre, to this vineyard that was under no-till and had a semi-permanent cover crop that was reseeded every year. So she applied the compost. The compost was broadcasted to the inter-rows, so the tractor rows and the undervine. And then she measured over 3 years the changes in soil carbon, emissions of greenhouse gases, crop yield, and grape quality. And so what we've seen in terms of carbon is that compost could increase carbon in the soil, but this depended on the depth of the soil sampling and the location within the vineyard. So in this graph here, we can see the concentration of active carbon in the soil at different depths, 0 to 6 inches, 6 to 12 inches, 12 to 24 inches in the tractor row or the vine row, and with increasing rates of compost application. Blue for 0 tons per acre, so this was our control. And then orange is 6 tons per acre. So what you've seen is that increasing the rate of compost application increased carbon in the soil significantly. But this was more remarkable in the 0 to 6 inch interval, so the top soil, and it was more remarkable in the tractor rows. So what we think is happening here is that there is a potential synergy between compost application and the cover crop. Those places where you already have a plant growing, that it's like basically pumping carbon from the atmosphere into the soil, if you fertilize a cover crop with compost, you could increase the amount of carbon that it's put in the soil substantially. So there's a potential synergy here between the compost and the cover crop. On the other hand, we didn't see increases in CO2 or N2O emissions, and we didn't see also any changes in grape yield and grape quality. So there were no negative effects of increasing compost application rates. So compost combined with cover crops and no-till could be an effective strategy to mitigate climate change in this case. The last question is, can regenerative farming keep grape yield and quality? And this is one of the biggest unknowns at the moment as well. Okay, we can increase organic matter, we can increase soil carbon and increase soil health, but how is this affecting my grape yield and my grape quality? Usually in a conventional vineyard, grape yield and grape quality, it's very directly dependent on inputs, external inputs of fertilizers that are directly driving the concentration of nitrogen, right? For example, in the soil, ammonium and nitrate, that will be taken up by the vine. There is very little reliance in these conventionally managed soils on the soil organic matter pool, right? So the potential amount of nitrogen that is released by this organic matter is very tiny, and the vines mostly rely on the fertilizer. In a regenerative system, what we're doing is trying to increase this pool of organic matter. You know, as we put compost, we put cover crops in the soil, we are basically beefing up the soil organic matter, increasing it, which also increases the potential of the organic matter to release ammonium and nitrate for the vine to use. So this could be positive if we reduce fertilizer inputs. But what happens if we keep practices as they are, right? Is there a negative effect for vine balance? Am I going to have consequences for grape quality, for example? So this is one of the biggest unknowns at the moment with regenerative practices. There are quite a few studies with compost. We saw the previous example where we didn't have negative effects, but there aren't that many samples with, for example, sheep grazing and animal integration. There aren't that many studies looking specifically at crop quality and crop yields. So what happens when we put an animal in the vineyard, right? There's different things, different ecological effects that could be driving nutrient cycling. So on one hand, the act of grazing, sheep grazing on cover crops has this compensatory growth on the cover crop, where the cover crop is going to try to grow back and produce a bunch of carbon compounds from the roots that are going to produce changes in the soil microbiome, the activity, the diversity, the abundance. And this is going to have consequences for cycling of elements, including cycling of nitrogen. Obviously, manure, it's a really good source of nitrogen. It has a lower C/N ratio. And so it could also be a source of available nitrogen for the plant. So are we increasing the pool of nitrate and ammonium in the soil to a way that we're changing the quality and the yield of the grapes, right? So we addressed this question in a trial that we did at Tablas Creek. Already a few years ago, we finished this trial in 2020. This was a till versus grazing trial. So we had a full factorial experimental design established. And we had these grazing enclosures that you can see here in orange. They were like fencing, plots that were fenced, where we had the sheep going and graze the cover crop completely 2 or 3 times a year. And then after the 3 years of doing this, we measure changes in soil carbon, we measure a bunch of different things, and also nutrient cycling, the soil microbiome, microbial activity, and grape quality. What we've seen is that exactly as we expected, grazing did increase microbial activity, and specifically it increased the activity of the enzymes that are involved in the cycling of organic compounds. So the cycling of carbon compounds like, glucosidase, cellobiase, the cycling of nitrogen compounds, phosphorus and carbon was increased by grazing treatments like we can see here in green as compared to non-grazing treatments, pretty much consistently for all of these enzymes that we looked at. What this is telling us is that grazing accelerates nutrient cycling, and potentially this could have negative effects for grape quality and yields. But when we went to look at yields and quality, we didn't see significant effects, right? So this is the yield, kilograms per vine, in till versus no-till plots, and graze versus no-graze within those till treatments. No difference whatsoever across these treatments in yield, clusters per vine, the same. They were all pretty similar. Same with anthocyanins and phenolics. They were all similar across the grazing treatments, whether they were tilled or not. So grazing could be a valid strategy then to support soil health. Doesn't seem to have negative effects for grape quality. But it has limitations. It is limited to dormancy, especially if your vineyard is not set up so that you can have the sheep in the vineyard during the growing season. So you basically need to raise your trellis. And that means that maybe we have to redesign vineyards for regenerative management. And this could have an increased cost, right? When we're changing things in the vineyard, which brings me to my last question, and I will wrap up quick. What is the bottom line? What is the cost or the benefit of using regenerative farming? And this is the work that Dr. Axel Herrera, as a postdoctoral researcher, also working in my group, it's doing with support from Foundation for Food and Agriculture Research, the CDFA, and also collaborating with Jackson Family Wines. He's doing a cost-benefit analysis of regenerative farming versus conventional management for 4 vineyards in Sonoma, established in Chardonnay, Pinot Noir, and Cabernet Sauvignon. So what he's doing is accounting for all costs involved in these 2 different types of management and all potential benefits, including change in nutrient inputs, carbon credits, change in yields, etc. So this is like a summary of some of his findings. This is the annual operation cost of the conventional scenario on the left, and the annual operational cost of regenerative scenario on the right. So the first thing we notice is that the large majority of the cost, operational cost, so that's like the cost of like just maintaining the vineyard year to year, is associated to labor in both types of management. There is also a big chunk of the cost that goes into indirect costs, so insurance, taxes, repairs, etc. And a very, very small proportion of the cost is associated with the actual management practices. So whereas in the regenerative scenario, we could have an increasing cost, from labor, there could be potentially more hours of labor dedicated to this management, especially at the beginning when learning the new management strategy. You could also have savings in inputs, agrochemical inputs, fertilizers, herbicides, pesticides, etc. So overall, the bottom line is that you could have slightly lower costs, operational costs with regenerative farming compared to conventional. But the overall scheme of things is that these savings are minimum because the majority of the cost that goes into vineyards, it's related to labor and indirect costs, not so much to these potential costs of the practices. All right, so summarizing, is regenerative the path forward for grape growing in California? Well, through these examples, these different projects that I showed you, we've seen that regenerative could be useful in adapting to extreme weather events and climate whiplash, reducing environmental pollution and mitigating climate change by promoting carbon sequestration. And also, it doesn't seem to have negative effects for grape quality when it's done right. So there is potential. There's also quite a lot more to do, just figuring out how all of these works in different environments, different soils, and in vineyards that have access to different resources, right? Thank you so much for your attention, and I'm happy to answer any questions. I hope we still have some time, but yeah.
We do have one question in the Q&A, and it is, was the carbon cost of making, delivering, applying compost factored against any differences in soil, carbon, or emissions? Is it net positive?
Yeah, we factor in the cost of trucking the compost, and of course that makes sense, you know, if you're buying local compost. If you are bringing compost across miles, then it doesn't make sense. So in this case, they use local compost, and the price of that was factored in. We didn't conduct a life cycle analysis, but that's something we are going to do. So emissions were not taken into account, you know, in the whole like carbon sequestration, you know, thing. So we are accounting for potential credits of carbon sequestration in the soil when applying compost and cover cropping. We haven't done a full life cycle analysis that also accounts for potential emissions of trucking, etc. That's something that we're gonna do next.
There's a couple also in the chat. So one is, what about using vermicompost to increase soil biomes? We practice that here in our vineyard in Paso, and they mentioned that your team sampled there.
Yeah, and I know that, I think this was led by Charlotte Decoq, and they did find also, interestingly, different effects of vermicompost than with compost. And vermicompost is really good for soil health as well. For supporting, you know, improving organic matter and supporting biological health, microbial activity and all that. Yeah.
One more quick question here. Any issues regarding compaction in vineyards that were grazed?
There could be, yeah. So it's one of the concerns of like grazing. If it's not done, if it's not done right, you could run into issues of compaction. You could also have issues of higher salinity from the urine of the sheep. So you have to be really careful. You can also actually have the sheep eat the grapes, which is something that I've seen in other trials that we have going on. And so like, especially the first years after adopting these practices, it's always like a trial period, right? Where the growers are learning how to implement the practices and optimize it. So it's very common to see decreases in yield, especially the first or second year after implementing these practices. And what is recommended is high intensity, short duration grazing, this rotational grazing, right?
So we have one last question, and I think this will be the last one, and we'll move on to the next speaker. Was the carbon added with the compost accounted for when showing the increased carbon in the soil?
Yes. And
Yeah, so it's like with the carbon added with the compost accounted for when, when showing the increased carbon in the soil.
yeah, it's a good question. When you add compost, you add carbon, right? And the more you add, and the more carbon you add. And what we've seen in the soil is an increase in carbon that is more than that. And we think it's because what the carbon is doing, and also all the other nutrients that you add with compost, it's supporting the growth of the cover crop, but also soil microorganisms, right? It's boosting the growth of other forms of life in the soil, which also brings carbon.
Great. Thank you very much. I really appreciate your being here today. And we all know Christina is actually going to teach class quite soon.
Yeah, yes.
So thank you
Right
for being
now.
the first speaker today.
Thank you so much.
Thank you. All right. Our next speaker is Mark Batney. He's the Water Management and Biometeorology Advisor for UC Cooperative Extension down in San Luis Obispo and Santa Barbara counties. And he's going to be talking about irrigation with recycled water.
Great. Thank you all very much. Karen,
Thank
can you
you.
see my screen?
Yes.
Okay, great. So the inspiration for this topic here, I'll kind of divide it into two here. Currently, Paso Robles, the city of Paso Robles, is underway with an important project to deliver recycled water, to produce kind of a tertiary quality recycled water, which will be available for use as irrigation for farms to the east of town here. So this is a really, of course, a very important thing for agriculture, given water scarcity conditions in all of Southern California, which we can define as everything south of Sacramento. You know, we really have to be cognizant of any new resource like this. And previously, the city treated the water minimally and put it into the Salinas River, but due to water quality concerns, that just was not a feasible option. So they really had to look at doing a higher level of treatment, which is quite expensive to do. So one way for them to recoup the cost of that is to then sell this water as an irrigation resource. So one of the questions that we have, though, or concerns, is that the quality of this water may be less than ideal. So we really have to be cognizant of the effects of water quality, potential impacts on a crop like wine grapes. You know, the Paso Robles region has really done an excellent job in developing a high-end wine grape industry in the area with some very high-quality wines that receive increasing attention. And I think the concern from my end would be, well, we don't want to put any of that at risk by potentially using a water which might impact the quality of those wines. So we just need to be very much aware of what the potential risks may be. And there are examples in the state of where recycled waters are used for wine grape irrigation. A really good one is up in Napa. But we really have to be careful that, you know, when we try to pull examples like that, the conditions are really not necessarily the same. You know, the quality of the recycled water may be very different. That's given the water that is going into that system and what comes out. And the rainfall conditions are certainly very different in that example. You know, in a region like that that might receive, you know, nearly double the rainfall every year, their use of irrigation water is much more limited, and that's going to then impact then the accumulation of anything that might be a negative factor in the soil and potentially in the grapes. So it's a more complicated thing sometimes than we would like. Well, the second part of this, of the inspiration, last fall, I was down in the Guadalupe Valley of Ensenada in Mexico as part of a UC team. We went down there to do a collaborative 2-day seminar on water management. A really very well attended and a very worthwhile event. If you've not been down there, that's a very dry region. Water scarcity is a big issue, and also water quality is a very big issue as well. So it's a very historic wine grape region. They've been growing grapes there for a very long time. It's a very small area, but one of their challenges is dealing with some very low quality waters for irrigation. And it's been recognized that some of the wines there are negatively impacted by salts. And so I'm very curious of what conditions in the vineyards lead to that effect in the wines. Now, I don't have very many wine drinking stories, But when we were down there at the end of this 2-day seminar, they put on a nice dinner for us. And I was at the end of the table with one of my UC colleagues and a couple of locals there enjoying the food. And a bottle of wine came to us. It was a red. And we opened that up and we each poured a glass. Well, we each took one sip of that wine. We put the glass down and poured it out without saying anything. And what made us all do that, that wine was so salty that we really could not drink it. And that's the very first time I've ever had an exposure to a wine that was really that heavily impacted by salts. And I have a pretty limited palate in that regard. So if it made me pour it out, then that really tells you something here. Now, I should point out that that was by no means representative of the wines that we drank there. Most of them were very good. But the fact that that can happen in some area vineyards, to me, is really important, that we need to figure out why that was happening. What are the conditions there that lead to that? And fundamentally, I would like to continue doing some work down there, kind of using that region as a test case for what can happen elsewhere in California here. Just because they are more advanced in dealing with salty conditions. When I say advanced, meaning that they have more severe conditions that we do here, I think we can really glean some very useful information for our industries here. So let's just kind of review some of the basics of water quality and irrigation here. So groundwaters, we know that most groundwaters contain varying levels of salts. This is just a representative example of the Paso Robles groundwater basin well qualities. This is some data that I took out from some studies that were done over 20 years ago now from that area, just characterizing different wells. And I think what this really shows you is that different wells have different levels of salts in them, as exemplified here by the electrical conductivity. So not all wells are equal, and we can put on these sort of different threshold values of where we have better quality water, waters with some increasing problem potential due to the salts, and waters which are very challenging. These very challenging waters with the high EC, typically we're not using those much for vineyard irrigation, in a few cases that we are, but I think for the most part, we prefer to have the lower salt waters for irrigation. So definitely it's well recognized here that we do have waters that we try to avoid for vineyards. Surface waters can also be a challenge for us as well in different parts of the world. Now, here locally, we're not using surface water, of course, but it's just, we do need to mention that it is a factor in other parts of the world. You know, the lower Colorado River is well known to be quite high in salt content. So for vineyards and other crops in the state which are using that water, it's definitely a concern here. This picture, it's actually a river flowing in Chile, the Mapocho, but I think you can just see visually. This is carrying quite a bit of salt, a lot of sediment, so very similar to what the Colorado River would be. In electrical conductivity, typically above 2 decisiemens per meter, high in chlorides. A water like this is being used for irrigation, it will have impacts on the crops that are grown with it. Now, the recycled water presents a whole different type of impact. So, this exists in many parts of the state. Increasingly, we're going to be using this. I mean, as one of the main new sources of irrigation water, this is something that we have to make better use of. But again, as I pointed out before, that the quality of this water is going to be dependent primarily on what the source water quality was. So if the source water quality, like in Paso Robles, is primarily coming from groundwater, whatever salts that water had are simply going to be transmitted through the system and come out in the recycled water as well. But you have other factors like what the municipalities are doing, the residents in those cities and elsewhere. Good example is if these residents are using water softeners to address the hardness in the water, well, they are adding fairly considerable amounts of sodium and chloride to that water, which will then be expressed in the recycled water. Things like this are what we really have to be a little bit concerned about. And I could envision going forward, and I think this is definitely happening in the state, that we will have more and more restrictions on the use of water softeners. That's already happening in some parts of the state where they're being prohibited from being used, simply from the standpoint of wanting to maintain more options with using that recycled water. So general impacts then on crops like wine grapes and others, we can look at when we add more salts to our soils, increasing the electrical conductivity of the soil. The main impact is once we increase beyond a certain threshold of conductivity in the soil, that we have a linear reduction in growth. And that's what I try to show with this slide here, that up until this threshold, which in this case is I put a little bit over 2, kind of representing maybe a typical rootstock response, the vines grow just fine. But once we exceed that threshold, then you see that linear reduction in growth. So in this case, the vines just produce less foliage and less production. You may not see any symptoms, visual symptoms on these vines that say that they are being affected by salts. The symptom is just simply less growth. So I was reminiscing here, about 20 years ago, about the year 2004, we had a lot of these types of symptoms showing up when we had those dry conditions back then. So these are certainly highly variable depending on the type of rainfall conditions that we have. The last several years, we've been very lucky with lots of rainfall, so I don't think we're going to be having to see this very often, but we know that our dry cycles will return, and this will be more expressive. A different effect is the toxic effect on the foliage. So this is typically due to high levels of chlorides, high levels of boron. This is a very different effect. In this example, these vines made very good vegetative growth. During the spring and summer, they looked great. Large canopies, large amounts of leaf area. But then as the season progressed and the accumulation of these chlorides and boron in those tissues increased, it gradually reached a level where it was just simply too toxic for those tissues, and they basically turned to potato chips. So these are two very different effects, one from a total salt content, and now this one from the specific toxicity effects that these components can have. Impacts on soils can be very important. And here we're primarily looking at the sodium content in the water and also the alkalinity of the water. So the image on the left in this drip irrigated system, where the sodium is being delivered to the soil in fairly high levels, you can see that dark ring that forms just beneath the drip emitter. That's a sign of that soil being impacted by sodium. What the sodium does, it destroys the micro aggregates in the soil. It disperses the soil particles. So what was once a soil that had good texture and infiltration, good structure and good infiltration and porosity characteristics becomes more and more like a brick. Very poor porosity, sealed pores, poor infiltration, poor aeration. So all things that we don't like to have in the soil. We correct that by adding more calcium to the soil. That just increases the cost of doing so. The picture on the right, think of that as sort of a vertical slice of a soil. Now you're looking at changes or variations in the pH of the soil. And what I think you can see there is beneath the vine row in this example, where this alkaline irrigation water was applied in this vineyard, that over time that changed the pH of the soil. Why? Because they were not acidifying this water sufficiently. So again, waters that have certain chemistry characteristics are going to change the chemistry of the soil over time. And increasing pH is problematic because that can create issues with nutrient availability, in particular, impacting vine growth. Other issues with water quality are problems with our water delivery systems, the drip irrigation system. So the picture on the left, those white precipitates, the mineral formation. We typically see that with water that's hard with calcium and magnesium bicarbonates and carbonates. That's an additional management headache for somebody to have to treat that water with acid to prevent that type of formation. Some waters also have iron and manganese as a clogging potential, which has a very different type of treatment method, typically through aeration. So depending on the quality of that water, that can create some additional management challenges for us. Some waters' biological component is very important. So the example on the right of flushing out that irrigation system more frequently to take care of that biological load that's being added to that system would be a key management step for that. Now, I'm very interested in the whole effect of, we can call it minerality So how does the alteration in the quality of the water, the salt content of the water, impact the salt content, let's say, of the crop? So here's a different vine crop, of course. This is grown in the deserts of northern Chile using some very salty water, which many other plants would not grow with it. But I had the chance to visit this a couple of years ago, and what really impressed me was the very good flavor of these tomatoes. And why is that? It's because they're being flavored essentially by the salty water. So this is an example where some crops, the salt content, the increased salt content could be seen as a positive thing if it gives you that salty flavor in the product where it's acceptable. And so in this case, kind of a pre-salted tomato, to me at least, seemed to be a very good thing. Other crops that may not be quite the same way. But what they do see when they're irrigating with these salty waters is a lower level of production, but given their limitations here, that's really all they can do. So there's a bigger question then about, salt content in wines themselves. So I'm really not aware here in California that this has been a concern that many of us have had. Talking to some of the local wineries too, it doesn't seem to be something on their radar as what they test for either. So I'm wondering though, if going forward, that might be something that we do need to at least start looking at, just to be aware of any changes that might be happening. And why is that? Well, in other parts of the world, think Australia, Argentina, Chile, South Africa, and Mexico, countries which really have growing conditions that are not too different from the parts of the Central Coast here, they do have issues with salt content in wines. So what are those factors that create these concerns in some of these areas here? Again, it's not all wines, of course, from these areas, but there are certain wines coming from these regions, which it's definitely a big concern. So fundamentally here, if we have now recycled water available to us, which has some level of salts, do we need to be very cognizant of the risks that this could pose to us? And again, the people who've made big investments in producing, very good wines from our area, I think that's something that we at least need to look at here. So what are these salty wines like? And this is some information from an article from Australia. They've done an awful lot of work on this. Character in wine, when you have these high salt content, well, flatness, savory, soapy, burning persistence, kind of not things that we would really want to associate, I think, with our wines that we're producing. Different countries have different legal thresholds for the amount of salt that can be in the wines here. So in Australia, they have 1,000 milligrams per liter, basically 1 gram per liter as sodium chloride, which would be equivalent to 606 milligrams per liter if you're measuring just the chloride content. Interestingly, you have different thresholds for whether it's white wine or red wine. And then you can just distinguish between a detection threshold where you first tend to sense that salt is there, and then another threshold, a recognition threshold, where you say, aha, this is salt. So again, different values here, and you can see then the detection threshold is quite a bit less than the legal limit in this case. And so I'm very curious here for a typical American consumers of wine, where our detection thresholds and recognition thresholds might be. I think this data comes from some work done in Australia, and I'd be very curious from different palates how we might approach this. So one of the issues in the Ensenada area in Mexico, some of those wines that to our palate might be fairly salty, to the palates there don't seem to come across that way. It's just they're either accustomed to that or it fits in better with the foods and things that they're enjoying that wine with. Okay. So what I'm showing you here, a while back, the Paso Robles Recycled Water Project produced an example of what the potential quality of the water might be from that system. And so the water sample was sent to the fruit growers lab. The fruit growers lab produced one of their very nice reports showing us here what we can expect potentially from that water. So the things that stand out, fairly high chloride content and also fairly high sodium content. So the two things that I have the arrows pointing at there. And again, considering the origin of the water that the city is using typically from groundwater, and then the potential to be adding sodium chloride for water softeners, it's not a surprise then that these two components could be fairly high in the recycled water. Other issues of concern, the high levels of bicarbonate, again, reflecting the origin of water. Also, it's fairly alkaline. pH. The EC level here, it's certainly higher, I'd say, than the typical irrigation waters used in our area, but there are vineyards that are using waters that are worse quality than this. So we do need to keep that in mind for perspective. Of course, we would like to have a better quality recycled water source, which we could achieve by blending with some other surface waters, but that would then raise the cost of the water. So we really need to look at how can we incorporate a water like this into our management systems. And so for me, one of the big questions is, well, what vineyard factors are going to be affecting the content in the wine? Rootstocks, we have a lot of information on tolerance to salinity, but less information on uptake of ions like chloride. Luckily, we do know that 1103 Paulson, which is our most popular rootstock, is very good at excluding chloride. So I think that's going to be a big factor in our favor. Variety effect, I think there's definitely some need for more information on that in our area. And then just really what levels of salinity and things like chloride in the irrigation water in the soil will lead to problems. And I should mention that in the Ensenada area, that some people think that this is mostly an issue due to ocean aerosols and not necessarily due to irrigation water quality. I'm not sure about that, but that's something that I think could be looked at. So part of my plan here is that I would like to be spending a bit more time in Ensenada, kind of using that area as a test case for what we can expect here in California going forward. Currently, there is some research, I believe, in conjunction with a French group, just looking at wine qualities in that area. But I'm not aware that they are connecting the issue of salt content in the wines back to vineyard conditions. And that's really what I would kind of like to look at there. I think that would be very useful information for us. So again, this is sort of a valuable test case, I think, for us here in California. And part of the work that I'm doing there is helping them understand their irrigation water quality. And that's a region where they've really done very little testing to understand what the quality of the water is like. So I'm trying to introduce that assistance there. This is my first example of well water that I was able to have tested in that area. And just looking at this, it's interesting. This water is somewhat similar to the recycled water coming from the city of Paso Robles, but a little bit saltier. So I think this, to me, is a really great example of how we can take information from a vineyard that's been irrigated with this water and then correlate that to our conditions here. So again, that to me is the value of doing this work internationally. I think both regions have an awful lot to gain from this. So thank you all very much for your attention. If you've not been into the Ensenada area, here's just a photo of what that region looks like. As you can see, a very dry area, but I'd highly recommend some time. It's not too far away, and if you would enjoy visiting, I'm sure they would appreciate it. All right, thank you very much.
Thank you, Mark. There is the first question. You may have actually shown some numbers here. Can you give some real numbers for EC chloride where you are starting to see toxicity from the water test sites? And I saw the chart for EC showing general trend, but it looks like you actually had some numbers there in some of these.
Yeah, so I've got the numbers on water quality, but as far as connecting, let's say, a water quality to expression in a vineyard, that is the question. And I mostly say looking at expression of as far as fruit and wine content of salts. But another thing we could look at is expression of salt symptoms, such as foliage burns, things like that.
All right, there's another question here. Extended rain is the best means to flush the salt from around the vine roots. In drier years, the recommendation is to do extended irrigation sets to flush the salts, which seems counterintuitive using the same water that caused the problem.
Yeah, no, good question. You know, it does seem counterintuitive, but what happens in the soil, you know, you irrigate with whatever water quality you have, but evaporation is removing pure water, leaving more salts in the soil at a higher concentration than what you irrigated with. So the soil water salinity will be higher than your irrigation water salinity. So if you add more of your salty irrigation water, you actually flush out those salts, and the end result is a lower salt content in the root zone, which is what we're trying to achieve.
All right, I think that's all the questions that we have.
Right,
Thank you very much. All right. Our next speaker is David Block, and he's a professor in both the departments of viticulture and enology and the Department of Chemical Engineering here at UC Davis. And he's going to be talking about advances in single vine resolution irrigation. Thank you, Dave.
Great. Thanks, Karen. So we've been working kind of steadily over the last 10 years in this area. It hasn't been a huge effort for us, but one that we've been working on for extended period of time now. And I think, you know, the reason what I'd like to do today is to first of all talk a little bit more about our motivation for going to higher resolution irrigation, possibly down to single vine resolution irrigation. That is delivering just the right amount of water to each vine. And then I want to talk about the two of the main components that we've been working on of a system that would do this. One is sensing evapotranspiration rates down to the single vine level. And then the other thing that we've been working on is how do you deliver water down to a single vine level? So that's kind of what I want to cover today. In terms of motivation, I think people, probably all of you understand that irrigation needs change spatially in a vineyard. It could be from topography, it could be from roguing for disease management in a vineyard. It could be from soils, heterogeneity in soils and so forth, or heterogeneity in plant material. And you know, currently most vineyards are irrigated in bulk, meaning most of the vines or all the vines in one irrigation block are delivered the same amount of water, even though they don't need it. So, you know, I think if you look at water use in a vineyard, it's high, maybe not as high as other crops in California, but it's high in a lot of areas of California. And those water resources are scarce. And so increasing the water use efficiency is another reason for thinking about higher resolution irrigation. And you know, I think that there are kind of add-on reasons for doing this. It's possible that if you could control the irrigation down to a finer level, that you might be able to improve quality by decreasing heterogeneity in the vineyard. I think that's still uh, an open point as to whether we know enough about that relationship to really dial in exactly what we want to do. But I think there's obviously been decades of work in that area to indicate directions that you could go if you could irrigate down to a higher resolution, even down to a single vine level. So the goals in the work that we started, and this is probably started 9 or 10 years ago, thinking about this, is that we want to be able to um, sense plant water status down to single vine resolution and deliver exactly the amount of water that that vine needs or that we want that vine to have down to the single vine level as well. And we want to be able to do that at, you know, as an initial goal down to $5 per vine or maybe even less. And the number that we chose there was based on, you know, increasing the amount it would cost to establish a vineyard generically in California by something on the order of something like 10 or 15%. We want to develop a system that's easy to install and maintain. And I'll show you some examples that we developed where it's definitely not the case, and somewhere we're getting more towards that ideal. And with the goal of giving vineyard managers in California a way of increasing water use efficiency and having more control over the quality of the grapes coming out. So when we're thinking about a next generation irrigation system, this is kind of what we're generically thinking about. And that's being able to have a sensor on each vine that's sensing the water status of that vine, determining how much water that vine is actually using or needs. And then another device on each vine that's delivering exactly the right amount of water to that vine. Obviously, there would be some connection here, either automated or through the farmer deciding how much water to deliver to each vine, dependent on the water status of that vine. So that's kind of generically what we're looking at. So this would be for each vine, and so each vine in a vineyard would have water sensing status, ET sensing, and a way of delivering the right amount of water. So I'm going to spend the rest of the talk talking a little bit about the sensing first, and then talking about where we are with water delivery. And I should say, and I didn't mention this on my first slide, this is work from a lot of graduate students and faculty members here at Davis and at the University of Michigan, and more recently at Verdi, which is a company based in British Columbia. All right, so let's talk about sensing first. Now, there are lots of methods that are out there for sensing evapotranspiration rates. Certainly, there are energy balance methods that are being used using different equipment out in the vineyard. Those are pretty common right now. Certainly, soil moisture sensors, sap flow sensors, another thing that are being used in vineyards. Using reference ET with crop coefficients, certainly a method that was pioneered by in California people in our department and others. More recently, people are looking at aerial imaging to get an idea of ET, and that usually requires some follow-on computation to go from the image to what the ET is predicted to be. I think in a lot of these methods, maybe all of them, there are still limitations, and there are limitations to what we're doing too. But I think some of the obvious limitations are ignoring that the management zone is going to have heterogeneity. Not all the vines are going to be the same. When we're measuring ET, lots of times we can only do it over acres, for instance, not down to the single vine level. And so in general, the data that we're getting on evapotranspiration is not at a fine enough level to know exactly what the ET is for a single vine. And if we can, in cases like sap flow sensors, what you're doing there is you're getting information on one vine, but you're assuming that that vine is representative of all the other vines in your vineyard that you're watering. So some of the work, or a bunch of the work that I'm going to talk about next on sensing, we published last fall in Eno 1, and this is where a lot of the data I'm going to talk about for this part comes from. And you can see the collaborators here, mostly from UC Davis, but with Mark Burns coming from the University of Michigan. So what we did to kind of work out sensing down to the single vine level is we set up for kind of weighing lysimeters. We have these full-grown Zinfandel vines in buckets. The bucket is on a scale, so we know exactly how much water we're adding and how much water is going through the vine as it's transpiring. To do the sensing that we're going to do, we needed to measure wind speed. So there's a wind speed sensor here, and we need to measure humidity and temperature and log all of the data. And so we have 4 of these vines. I'm going to show you data from some of the vines as we go through, and I can and show you what some of the results from our single vine sensing. So in order to do single fine sensing, basically we're measuring these parameters on each of these vines, and then we have to be able to predict what evapotranspiration is based on that. And we did this using 3 models that I have listed here: the convective mass transfer model, the mass balance model, and a strictly empirical model. And what I want to do is just spend a couple of minutes talking about each one, and there's more information on this in the publication if you want to learn more about it. So in a mass balance approach, which is different than kind of the energy approaches that are used in, let's say, Thule Technologies kind of thing, what we're looking at is basically a mass balance approach. And that means that if we have a vine, we can measure the amount of water, the rate at which water is entering that vine canopy, and we can measure the amount of water leaving that canopy. And the difference between the amount entering and the amount leaving is the amount that's being transpired by that vine. And so you can go through the math to figure out what you need to measure for this. And essentially what you need to measure things like the wind speed, which is the V here, and the humidity, both in and out. And if you do that, you should be able to get an idea of the evapotranspiration. And the second method, we're looking at this as convective mass transfer. So what that means is convection is that you have, let's say, air blowing across a leaf. And if you think of the leaf as kind of a flat plane and wind blowing across it, if we think about that, the surface of that leaf being saturated with water and some ambient humidity far away from that vine, and we look at the airflow across it, then people have done, mainly chemical engineers, mechanical engineers, have looked at what are the factors involved in how quickly that water leaves the surface. And certainly it's a function of the difference in humidity between the saturation level at the leaf and the ambient. But given the engineering analysis with dimensionless numbers, essentially it's also going to be a function of the velocity of that air and the temperature. And so we can use this approach as well. And then we can just make up an equation, in this case, that's a function of velocity and temperature, and find these coefficients, and it's just a correlation. And we can look at, which one of these models, or if all these models might work. So to do that, first we have to measure ET. We have to know what the ET is on each of these vines. And the way we did that was we looked at the weight. And so for one of these vines, you can see here's a watering event in that vine. The weight goes up. And then you can see it slowly goes down over time. At nighttime, you don't get much of evapotranspiration. So the weight stays about the same. And then during the day, you get more rapid decrease. And if you take the slope of that, that's basically how quickly the water is going through the vine, or the ET rate. And what I've plotted in the bottom is, over the course of 4 days, what does the evapotranspiration rate look like? And we can essentially measure this exactly for these 4 vines. And so when we do that, in each of these 4 vines, we have research grade sensors. These sensors, humidity, temperature, wind speed, and so forth, are hundreds of dollars a piece. So this is not a practical solution in itself for estimating ET in a single vine level. But we can use these to kind of figure out whether these models work or not. So this is just data showing, sorry about that, data showing the meteorological data for one of the vines. And you can see over the course of 4 days, the wind speed varies. There's certainly a diurnal response to that. You can see temperature inside and outside the vine, and here on the bottom is the relative humidity. And so we're measuring that with these research grade sensors, and then we can use the different models to see whether we can predict ET. So on this next slide, all the purple on here are the actual ET measurements with the scale for each of these vines. And these represent data for 3 different vines. And this is data over the course of 5 days. And what you can see is in the top row, these are the predictions using the convective mass transfer model. In the middle row, these are using the mass balance model. And in the bottom row, this is that purely empirical model. And what you can see is there is some fit. It's certainly not perfect at this point, but some fit during these 5 days that we have on here. However, having said that, we've actually did this over the course of 2 years throughout the growing seasons in 20 and 21. And what you can see here, there's a lot of information, but what I would focus on are these R squareds. And this is how well the model fits. The closer it is to 1, the better the model is at predicting the ET. And I have data for vine 1 and vine 2 here. And what you can see is for the convective mass transfer model, the R squareds are somewhere in the 0.7 to 0.8 range, for a little bit lower on the vine 2, from 0.6 to 0.8, a little over 0.8. So pretty reasonable prediction to give you just an idea of what the evapotranspiration rate. Certainly not perfect, but it gives you a fairly good idea of evapotranspiration rate. If we look at the mass balance model, interestingly, for vine 1, the predictions are actually pretty good. And for vine 2, predictions are not really good at all at any time during either of those growing seasons. It's kind of interesting. We don't really know why this is. We're kind of trying to think about this now. Could be a sensor issue, could be something with the vine physiology, but certainly unlike the CMT model where both vines have pretty good correlation, mass balance model less so. I will point out mass balance model, one of the differences between those models is the mass balance model depends on the relative humidity sensors in each of those vines, and the CMT doesn't. And so it could definitely have something to do with the humidity sensors or placement of the humidity sensors. And then for the empirical model, you actually get a fairly good fit for both of them. I think one of the things that we worry about a little bit with the empirical model is that it worked really well with these vines in a bucket. But because they're not based on first principles like the other models, we don't know how well they're going to do when you put them someplace else in a trellised system and so forth. So that's going to take some more studying. So given that we get pretty reasonable prediction of evapotranspiration rate down to a single vine level, there is a question of, is this ever going to be useful? Because at something like $400 to $600 a vine for sensing apparatus, it's certainly not going to be cost effective. And this is where we started working with the University of Michigan, Mark Burns' group there. He's in the chemical engineering department, and he can actually take all of those sensors that we had in the vine and put them on one small chip that's about 1 centimeter square. And you can put it in a 3D printed housing for that, which is a couple centimeters squared, and with a hook on the top, with the idea that what if you can just hook this on the guide wire? His estimates are that we can definitely reduce the cost down a factor of 100, which would put us in the right ballpark. Probably need to go a little less expensive than that, but it's the right ballpark. And so if we could use a sensor like this that's mass produced, hang it on the guide wire in the canopy, then it could be that we could sense evapotranspiration at a reasonable cost down to single vine level. And they've gone through, at Michigan, they gave us a second generation that we tried out in the vineyard. The sensor you can see hanging up here on the guide wire. This is now the electronics, which are too large so far, and the power supply, again, too large. But what we're trying to do is go from these very expensive, very large sensors down to miniaturizing this and making it less expensive so it can be used practically. So that's kind of where we are with the sensing part. With water delivery, so this is the idea of if you could actually measure evapotranspiration at a reasonable cost down to single vine level, could you actually get a different amount of water in every vine? And again, doing this in a cost-effective manner. When we first started doing this, we actually started with this before we started with sensing. And we created a system out at Oakville Station in this vineyard block, which was all Cabernet, um, uh, on I think it was all Clone 8 Cabernet. Um, and I think it was either one or two rootstocks. We chose this because there was quite a bit of heterogeneity. There'd been a bunch of testing on there with cane versus cordon pruned vines and different cover crop trials and so forth. And so if you look at the NDVI from that, you can see there's quite a bit of heterogeneity there. So we decided, what if we could actually build a system and deliver a different amount of water, at least to 640 of the vines in this block. All right, so you can line up the NDVI this way with the block. So the goals there, because this was really the first attempt, was to get the irrigation down to single vine level, have it be really low power so that we can just have the whole thing be battery operated, no running wires through the vineyard, and to have wireless communication so we could address, irrigation to each vine remotely. So that was kind of the goals. Since this was just kind of our first attempt, we got 10 undergrads that were either mechanical engineers or electrical engineers to work on this. And there was this 4 faculty, and we got the idea and decided, let's do it as fast as possible. And so in 2 months, we got the system out into the vineyard in Oakville, that would irrigate 640 vines individually. Doing it fast meant that we had to use equipment that was readily available. And so if this looks like we went to Home Depot and bought parts, that's almost exactly what we did. Most of these parts we could find at Home Depot. The valves are actually the valves that are used on Delta faucets, kitchen faucets, the ones that you touch and they turn on, or you touch and they turn off. And there's a single valve in here for delivering water to each vine that we were controlling, the 640 vines. So basically, each row had 32 vines. Each of these panels controlled water to 8 vines, and so you needed 4 of them, 4 of these panels at the end of each vine to control all the vines in a row. And with Andre Knudsen in electrical engineering, he also designed the controllers for this, did all the soldering and so forth to get a controller in each of these boxes. And this is what the boxes looked like. We tucked them into the end of the vine row here. We connected the manifold to the existing irrigation line. And then what we had to do was, from each of those valves, we had to run irrigation tubing. And it was probably about, 11 miles of tubing that we put in. This is not easy to install, but it was really proof of concept. And we were able to control water to 640 individual vines. At the time, we set it up as blocks 1, 3, and 5 were controlled automatically. Block 2 and 4 were controlled just with kind of normal conventional control. And we were able to do this for 2 years before the block got a huge amount of red blotch and we had to stop. But it was proof of concept, and we learned a lot from doing this. We learned that it is possible to deliver water to individual vines in a vineyard using just battery-powered equipment and to control it from a distance. So that was good. We also learned you need really good information to know how much water to deliver, and lots of times that's not straightforward, as I discussed in the sensor part. We learned that you should develop a system that works with current irrigation equipment, because running 11 miles of irrigation tubing in a plot that was a little over an acre is not a good idea and not going to be cost effective. And the system needs to be really robust. We dealt with ants and snakes and rodents and dust and all kinds of things that helped us figure that out. I'm sure that's obvious to you. Okay, so the next generation we've been working on again at the University of Michigan and Mark Burns' lab. Brian Jenkins is the engineer that's been working on this with him mostly. And this is kind of what the next generation looks like. In this case, if this is your irrigation tubing where it says A, and you have a emitter, standard off-the-shelf emitter, sticking out of that irrigation tube, basically the device that Mark's lab developed just snaps right on to that emitter and controls the water to the vine. This is a little solenoid valve. They've also developed very small flow meters. So C here is a flow sensor, and that will help because you will know exactly how much water you delivered to the vine, controlling it with the solenoid valve. All right. So this is kind of the next concept. Again, it would snap right on. Mark has done, and Brian have done some testing with a system with just 10 emitters. And to each of those 10 emitters, they programmed the system to deliver a different amount of water. The amount of water they were intending is in blue. The amount that they delivered is in orange, and you can see works really well, at least in Brian's backyard in Michigan. Right. So at this point, and I will say a lot of this work was funded through the state of Michigan that was interested in having technology developed in Michigan that could be commercialized. And after doing this work, basically what we decided was we thought about, should we commercialize this or work with a company? And what we ended up doing is to start a collaboration again between Davis and Michigan, but with Verity, this company that already works on irrigation management. And so we started this collaboration a little less than a year ago. And Verity already makes tools for automating irrigation, not only for vineyards, but other crops. And you can go to their website and look at it. I have no interest in financial interest in them. We're just collaborating on this project. But just as they're already working with growers, including grape growers, on automating irrigation. Not down to the single vine level. That's what they're working with us on, or single plant level, but they are working on irrigation at the row level and block level. And that's already out there. So they have technology that looks like this, where they're controlling irrigation with these irrigation lines with solenoid valves. In this case, everything downstream of that irrigation line would get the same amount of water, but you can start to have higher resolution than just block resolution. It could be by row or by irrigation zone. And this is just a picture of one of their installations in a vineyard. This is not down to the single vine level yet. This is more in zone. But again, what we're trying to do is to work with them and take using the technology that we developed for automating the drip irrigation, controlling drip irrigation with what they've already developed. In addition, they also develop software that can help manage all of their hardware and also interfaces with sensors from other suppliers and so forth, so that if we can, well, we are continuing to develop this irrigation technology. The idea is that eventually you would be able to use software like theirs or from other companies along with these controllable emitters, remotely controllable emitters, to actually do all of your irrigation scheduling and to irrigate based on how much single vines or single regions within your vineyard, how much water they need. All right, so with that, I've talked a little bit about what we're doing to sense down to the single vine level, and how to deliver water down to the single vine level and where we're going with that. I want to acknowledge the funding sources, including the Dow chair that I have in the department. MTRAC is the funding from the state of Michigan, and Verity, and some early funding from Cypress Semiconductor and some other donors. And so with that, I will stop there and see if there are any questions.
There is one, and someone's interested in a cost benefit analysis. What is your target winery, excuse me, for a single vine irrigation system?
Yeah, I think it's a really important question. Like, if we're at $100 a vine, it's not really going to make sense for anybody. If we're at $5 a vine, including the sensing and the delivery, in my calculation, based on planting costs at Oakville for us, it's about it would be somewhere in the 10 to 15% premium cost, but being able to basically for the life of that vineyard control down to the single vine level. Of course, your costs can be cut by not going down to single vine level, but by going to groups of vines. And I think if we're talking about Central Coast, probably similar. If we're going to Central Valley and maybe your planting costs are less, getting down to $2 per vine or something will allow you to do that with not much premium in the cost. And then it's going to be a matter of, thinking about how you're irrigating now and deciding, how much you want to be able to control to a higher resolution, either because you're consistently roguing for and putting in new plants for disease control, or you have a lot of heterogeneity and you wish you weren't quite as heterogeneous in your vineyard. Then it's going to depend on vineyard managers and wineries really thinking about the cost benefit analysis of that extra cost. So we're not down to 10, 15% extra cost yet. It's still more expensive than that. But that's the goal. And, the estimates that I've seen with Verity, I think it's going to be possible to do that. And so that's kind of the goal and where those numbers came from.
Thank you very much. We're at about 10:32, so I think we'll take, roughly 10 minutes and then start our way back here so that we're ready to start right at 10:45. And we look forward to seeing you all here in about 10 minutes. Hey there, Matt.
Okay, Karen, did you want me to start sharing my screen?
Sure.
Okay,
We'll wait another couple of minutes till we actually start, but that's probably good. Yeah.
okay, that's what I figured.
Thank you.
So you can see my screen, right?
Yep.
Okay,
Looks
good.
good.
We had an absolute downpour here about half an hour ago. I'm at my mom's place in San Diego.
Ah,
It was hailing and just pouring like crazy.
sounds like our weather yesterday.
Huh.
You know, there was an earthquake up near Lake Almanor yesterday at about it was 6:34. We didn't feel it in Davis, but people in Sacramento felt it. And then I saw this morning there was a similar level over centered in New Jersey on the
Yeah, I
east.
saw that. That's crazy. They're not used to it there.
Mm-mm. So we got one more minute or so, and then we'll get started with the second half.
Okay, sounds good.
Well, I hope everybody enjoyed the break. I sort of ran around the building a little, getting up from the chair after sitting for a while. So it's kind of nice to have a little break. And I think we're just about ready to get started here time-wise. Yep, there it is. So we'll start the second half. Thank you, Matt, for being here today. This is Matt Fidelopoulos. He's a professor of cooperative extension in viticulture in the Department of Viticulture and Enology at UC Davis. And today he's going to be speaking about grapevine mineral nutrition. Thank you, Matt.
Okay.
Take it away.
Thank you, Karen. Well, before I begin, I just wanted to acknowledge Pete Christensen, who was an extension specialist in the department before I started, because he developed much of the mineral nutrition and diagnostic information that we still use today, even though we've been trying to update in these tests. It's amazing how long they've persisted, and for good reason. So when we think of essential elements that grapevines need in California, these are the ones that we most often encounter problems with. The macronutrients, nitrogen, potassium, phosphorus, and magnesium, and certain micronutrients, zinc, boron, iron, and manganese. And the main difference between a macronutrient and a micronutrient is not their essential nature to the plants. So if any of these minerals are deficient, the plant will fail to thrive, or they will not be at optimum production. But really, the difference between macro and micronutrients is the quantity of nutrients needed with these different minerals. So you can see this chart here shows the relative amounts of these different nutrients that we quantified in the annual growth of table grape variety, Valley Pearl. And you can see things like potassium, calcium, nitrogen are needed in high amounts, and things like phosphorus, magnesium, much less, and zinc and boron, we could not even show on the same scale as these other nutrients. So that doesn't mean zinc and boron are less important than, say, potassium, but they're just needed in smaller amounts. So a popular strategy in nutrition, vineyard nutrition, is a replacement strategy. So if your vines are already in a good state in terms of their nutrient content, then you can go several seasons often just by replacing the amount of nutrients that are taken out of the vineyard and fruit. And here is a table of sort of average data that was compiled, I believe, by Larry Williams. And just looking again at the macronutrients, potassium, nitrogen, calcium, phosphorus, and magnesium, you can see they there's a higher quantity of those nutrients in a ton of grapes compared to the micronutrients, which are just present in trace amounts. And anyways, as a replacement strategy for nitrogen fertilization, this can be a good starting point to get you in the right ballpark. Now, of the macro and micronutrients that we typically or that we think may require attention in some parts of California, in my area in the San Joaquin Valley, the nutrients that are most often deficient are nitrogen, potassium, magnesium, zinc, and boron. And those are the ones I'm going to talk about the most for the rest of the presentation here. So when we talk about managing nitrogen, acceptable vine vigor, that's one of the big questions to ask yourself. If the vines are growing well, they're filling out the trellis in a reasonable amount of time, they probably have enough nitrogen. If they're severely deficient, which is something that you rarely see in California vineyards, but if they were, then the vines would start becoming chlorotic. That is, they would lack green color, and they would tend to have small leaves and limited shoot growth. And I've also seen in very deficient vines that you start to see anthocyanin accumulation and organs that don't normally show this. So for example, the rachis or even the petioles may be strongly pink colored. Now on the opposite end, vines with excess N, which is much more common than not enough N, you'll have rank growth. So the vines will just be growing like crazy with long internodes and dark green leaves and large leaves, lots of lateral shoots often. And more often you're somewhere in between that. Excess N, it's easy to know that you have too much N just by the rank growth. Severely deficient, again, that's easy to tell, but it's in between where tissue analysis is helpful for verifying the N status and give you some feedback on your nutrition program. The other thing people need to know is how much N is needed and when should be applied. And I think it's important for people to review their fertilizer history and the N contributions and losses, and also consider the rootstock and the root condition when they're making fertilizer recommendations. This picture here is actually one of our panelists, Mark Batney. This was taken in a vineyard in Argentina. And the reason why I like to show it in this presentation is you can see how dark it is there. Well, this is on a bright sunny day in the middle of the day, kind of an overhead vineyard. Mark's standing on a big pile of leaves that have already been shed from the canopy, and the canopy itself is probably several feet thick. And so he's just looking for light there. And we asked the growers about their fertilizer plan and in particular nitrogen, and they were fertilizing with nitrogen. And when we asked them why, they said because the lab test tissue results were indicating that it was needed. So you cannot go only by tissue tests, but they're helpful in companion or in combination with visual observations. So here's a less dramatic comparison of higher versus lower nitrogen status in a commercial table grape vineyard. The vines on the left there have not been fertilized for several years, and you can see that the canopy is kind of sparse. The leaves are kind of yellowish, and the vines on the right, which have been receiving about the amount of nitrogen that they accumulate every season in the leaves, stems, and fruit, kind of a complete replacement, not just the fruit, but also the leaves and stems. They have a much fuller canopy, much less, you cannot see through it nearly as easily as the deficient vines. And if you look at the shade underneath the vines, you can see it's much denser on the vines on the right as compared to the vines on the left. Here's just a different view of the same vines, showing the color differences and also the sparseness of the canopy better. And maybe depending on your monitor, you might be able to see there's differences in berry size too. And then again, a representative leaf of both canopies, showing the smaller and more chlorotic leaves of the deficient vines and the darker leaves of the sufficient ones. Here are some laboratory analysis guidelines. These happen to be for nitrate, nitrogen, and petioles at bloom. And it's important to note that the standards are different if you're using petioles versus leaves. And the relationship between petioles and leaves is usually, there's usually a distinct relationship there, but it varies from variety to variety and vineyard to vineyard. So if you currently are using something like petioles for your analysis, it's probably best to continue to do that, or to have some period where you transition to blades where you're collecting both tissues so you can see how they're related in the property that you're managing. And it's important to remember that nitrogen utilization is dynamic. So vines store and remobilize N from their storage organs, and stored N can provide up to 30% of the N used between bud break and bloom. And for that reason, spring levels can be strongly influenced by the nitrogen status in the previous summer and fall. Pete Christensen had done some work to show that post-harvest applications of N can be effective, but they really should be reserved for early to mid-season varieties. If you shouldn't apply nitrogen post-harvest in a late season variety or in a growing region where the time between harvest and senescence of the canopy is short, because there won't be enough time for the N to be taken up and stored. So spring to summer is really the best time to apply nitrogen, because that's when the vines really need it and are putting it to use. And it's always beneficial to apply in increments over time. That reduces leaching. And also irrigating at less than or equal to evapotranspiration is also helpful to avoid leaching of N. Post-harvest, as I mentioned before, it's okay for early to mid varieties that still have an intact, healthy leaf area with at least 3 weeks or a month or even more before leaf fall. These are the different nitrogen losses that you can have in vineyards: volatilization, leaching, and crop removal. So crop removal, we estimate overall, there's a lot of variation from vineyard to vineyard and season to season, but in general, it seems like most of the varieties that we grow here are taking about 3 pounds of N per ton of fruit harvested. So about 30 pounds of N per acre if you have a 10-ton crop per acre. As we mentioned, spring to early summer or post-harvest are probably the best times to be applying nitrogen. Spring to early summer, really my preference, because that's when the nitrogen is actually being put to use. These were just some sort of rules of thumb that Pete Christensen put together. If you have high to excess vigor, don't even fertilize with N at all. High to medium, maybe you don't even need to replace all of the N that's being taken out of the fruit. As you get into medium or medium to low vigor, you need to be thinking about replacing the N that's in the fruit, or even replacing more than the N that's in the fruit. If you have a low vigor vineyard and you only apply the N that's taken out from harvest, then you'll be kind of treading water or even losing the nitrogen status of your vines over time. So that's why you may even need to apply more than was taken out by harvest. So ways that you can minimize leaching: cover crops, fertilizer timing, placement. Not many people throw irrigating anymore. Most of us, especially in wine grapes, are drip irrigating, and that improves efficiency. And then irrigating an appropriate amount. So when we talk about potassium, potassium is among the Earth's most abundant elements. So soils typically contain 0.5 to 2.5% K, and that can amount to 100,000 pounds per acre foot of soil. So it's a lot of N in the soil, but most of it, a lot of K in the soil, but most of it is bound in rocks or fixed in clay minerals and unavailable to the plants. And the plants, what they need to take up is actually the ionic form of potassium, which is normally in soils adsorbed onto surface colloids or in solution. And it's important to know that potassium moves through the soil by diffusion and solution. And diffusion is very slow. And if you have rapid uptake of K, as often happens during the middle of the summer when the fruit are ripening, the potassium in the soil solution can actually become depleted around the roots. And also what happens during the middle of the summer, frequently, especially in wine grape vineyards, is that you start imparting a deficit irrigation situation to the vines. And when that happens, the water films around the particles narrow as the soil is dry, and that increases the path length that potassium ions have to follow to get to the roots. And drying is further increases soil fixation of K. And so you can see that all these things together, soil moisture strongly affects K availability. Now, potassium is taken up by the roots and sent to the leaves via the xylem, but in the leaves, K is loaded into the phloem and then transported to areas around the plant that need it, according to demand. So in that way, you have kind of a potassium cycle within the vine, and it gives the vine some feedback on to how much K is actually needed. And between bud break and bloom, most of the potassium is directed to leaves and stems. But after bloom, the fruits become a major K sink. So a sink is an organ that's accumulating or has a lot of demand for a certain nutrient, for example, in this case, K. And after veraison, more than 50% of the potassium amassed by the fruit may actually be drawn from the leaves, stems, trunk, and roots. And I think this is why you start to see in the middle of the summer in vines that have marginal potassium status or low potassium status, the deficiency symptoms of K, which are a type of chlorosis and a certain pattern on the vines. And it's because those leaves are shedding potassium to supply the demand from the fruit that may not be met from new K being taken up by the plant. So here is like a graphical representation of this. These are some data that were collected in South Africa some time ago, but we've collected our own data more recently, and they match up with this to a good extent. And you can see this horizontal lines here in this graph. Well, first of all, this is the K content of the vine in grams. So this is the vertical axis, and the horizontal axis is the sampling date. And you can see that after bloom, well, between bud burst and bloom, the leaves and the shoots are accumulating a lot of potassium. And the trunk and the roots only reduce their potassium content slightly. So unlike the situation with nitrogen, potassium, much of the K that goes to the annual growth of the vines actually is taken up by the roots that year. So it's not necessarily coming from stored reserves. But from bud break to bloom, you have a high demand for the shoots and leaves. And then after bloom, the biggest demand comes from the bunches. And you can see between veraison and harvest that you see a decrease in the K content of the leaves and the stems, and an increase in the bunches. And that's because some of the K that's being needed to meet the fruit demand is coming from the leaves and the stems. These are some data that were taken more close to home in Oakville. And these are similar kind of data, potassium uptake in grams per vine and days after flowering. And then you can see the different organs. And in this case, we are seeing, again, a big increase in fruit, or clusters, which are the black squares there. As we get later into the season, they really start accumulating a lot of K, and it comes at the expense of the leaves and the stems, which are these X's and circles. So similar to what we showed in that early historical data from South Africa. And then here's some data we took a few years ago in Shafter, which is in the southern San Joaquin Valley, and this is on table grapes. And here in this vineyard, the leaves are, the quantity of potassium in leaves is shown in the green lines, stems, the brown, and the purple color there is the clusters. And again, it's the same kind of story. There is a big increase in the demand by the fruit after bloom. And after veraison, we see a decline in the K content of leaves and stems. Now, part of this is due to shoot trimming that occurs around veraison, but that doesn't explain the full decrease. The rest of it is actually just translocation to the fruit. Now, there's different kinds of potassium deficiency, or I should say, different reasons for why we see potassium deficiency. So in a true deficiency, the soil has low availability of K. So certain kinds of parent material of the soils are just naturally low in K, or they're strong K fixers. And also, if you have shallow soils, you tend to see a lack of K available to the plant. But I think it's much more common that you see an induced deficiency of K. And that's where you have root problems like pests, drainage, or compaction that are affecting the ability of the plants to take up K. Water stress, as we talked about, is a major contributor. And also a very heavy crop that requires more K more quickly than can be taken up from the soil. Potassium deficiency can kind of look different depending on the variety. So here's an example from Chardonnay. But generally what we see is a chlorotic pattern around the margin of the leaves. So that's where you first start to see potassium deficiency. And it's usually kind of indistinct. So it's kind of like a washed out pattern in contrast with magnesium, which is much more sharp division between the chlorotic and the dark green. And as it gets worse, then the margin, the chlorotic portion starts to go in between the veins of the leaf and spread toward the center of the leaf. In colored varieties like Cabernet Franc shown here, you will often see red pigment developing in the chlorotic areas. So how can you manage K in the vineyard? Tissue analysis is very important in potassium deficiency for managing K. How much do the vines need? Irrigation, rootstocks, interactions with other nutrients and fertilizer practice. We'll talk about that. So here are some critical levels for K at different stages, bloom versus veraison. I think if you have a history of seeing K deficiency in your vineyards, then you want to definitely be into the adequate or even the cushion status at bloom to prevent a deficiency later in the season. So here is some K data we collected in various table grape varieties in different vineyards. Each column is either a different variety or a different vineyard. And you can see there's a lot of variation from vineyard to vineyard. It has to do with the biomass that's produced in each vineyard by the different varieties. This first row here shows the total K at harvest. This is grams per vine in leaves, stems, and fruit. The next row shows the total K in pounds per acre. So before it was grams per vine. And then we have fruits. This is the percent dry weight. So how much of the dry weight of the fruit is potassium. And then you can see on a pounds per acre basis how much of the K was in fruit at harvest. So it's anywhere in these table grape examples from 60 to 120 pounds of K is being taken out in the fruit at harvest. Okay, we already mentioned how K moves through the soil by diffusion and via water films. The dry soil increases the diffusion path length. So K uptake is strongly correlated with water use. And water strongly affects release of K from organic matter. We also talked about rootstocks, or maybe I just mentioned that there's a rootstock effect. Here you can see how different rootstocks have been placed into high, medium, or low status, I guess. These are how these rootstocks infer the potassium nutrition of the cyans. Mark mentioned earlier that 11F3P being one of the more common rootstocks used right now, and you can see it tends to impart kind of a low potassium status to the vines. So if you're on a site where you know potassium could be an issue, it's choosing a rootstock could be part of the equation there and helping to manage it. There are interactions with potassium and other nutrients. For example, nitrogen, magnesium, and calcium fertilizers can all affect K uptake. Nitrate tends to promote K, but ammonium can suppress it. And there's also a growth dilution of K with high N. And then calcium and magnesium can reduce K uptake. But usually it's not seriously affected unless you're marginal in terms of your K status. And then calcium and magnesium applications can negatively affect K. Okay, there's fertilizer practice. The key here is the efficiency of K application improves as the K is put closer to the root system. And drip can be very effective for that reason. And the reason why is if you put the K far away from the area where it's being actively taken up, then it has to satisfy the K fixation of the soil in between where it's being applied and where it's being taken up. There's different potassium fertilizers out there that can be used, and they all have their different pros and cons. So I'll just make note of that, and this is going to be recorded so you can go and take a look at this table later at your leisure. I want to spend a few minutes talking about magnesium deficiency. Normally, you don't see a deficiency like this one. This is on a special soil that had a lot of chemical problems that were man-made. It was on the site of a vineyard that was made on the site of a cannery wastewater discharge area. And so there was a lot of potassium lye that was applied to the soil. And here you can see how potassium, magnesium, and calcium all kind of interact and affect each other. In this case, massive amounts of K was affecting magnesium uptake. Anyways, put this on here mainly to show what magnesium deficiency looks like in leaves. Also a marginal chlorosis, but a much more distinct transition between the chlorotic part of the leaf and the one that has a normal amount of green color. And the reason why this occurs is magnesium is a primary constituent of chlorophyll. And so the deficiency does cause chlorosis in that very distinct kind of Christmas tree pattern that we just showed a picture of. And the deficiencies are most common on certain soils like sandy, weathered, or reclaimed alkali soils, as in the case of this wastewater site that we just showed, and in fill soils. And magnesium is moderately leachable, and so it may become more abundant in the subsoil. And young vines tend to be more prone to magnesium deficiency because the root sizes are smaller and they may not have grown to the point of penetrating subsoil. And so you're going to have to pay more attention to magnesium on young vines usually than you will on older vines. As we mentioned, this is just a description of the chlorosis. It begins as a narrow, distinct band around the margin of the leaves in mid to late summer, and usually on the basal leaves because magnesium is pretty mobile in the plant. And so as the vine needs more magnesium, it'll tend to draw on it from the basal leaves first. Here's some data showing the seasonal magnesium uptake in leaves, stems, and clusters. And you can see that most of the magnesium is in leaves, next in stems, and then clusters start to accumulate magnesium after bloom, but they never accumulate so much as is going to be in the leaves or the stems. Because of the mobile nature of magnesium in the soil analysis is usually inadequate to predict magnesium availability. And so bloom time petiole samples are preferred. Bloom time, because you remember you're going to start seeing deficiencies in the middle of the summer. So it'd be good to be able to do something about it. Less than 0.2% is considered deficient, 0.2 to 0.3 questionable, and more than 0.3 is considered adequate. If you just have mild deficiencies every summer, just in a few vines here and there, you can probably just ignore it. It's not going to have any commercial effect. If you're furrow irrigating, which most people aren't, but there are still some in my area, then you require large amounts to try to overcome this problem. Drip irrigation is far more efficient. There's other formulations besides magnesium sulfate, and you'll just have to consult with a PCA and choose the product that works best for you and follow those application recommendations. So seasonal zinc accumulation. Zinc is another really important micronutrient that can cause major problems, especially in the San Joaquin Valley. These are some data that we collected in different table grape varieties, Valley Pearl on the left and Allison on the right. You can see they're kind of different looking, and I'm not sure yet whether that's a varietal difference or just a site difference. So we're collecting more data to to see how much variation there is from vineyard to vineyard of the same variety. But most of the zinc is accumulated in leaves, less so in stems, and very little in the fruit. That was kind of a similar story as magnesium. But these charts don't tell the whole story, because it's very, very important that you have adequate zinc nutrition be going into bloom, because it has a big effect on fruit set and fruit size. So zinc deficiency is most commonly in sandy areas, or areas that have thin soil, cut areas. Some other factors that affect it, for example, rootstocks. Freedom rootstock tends to be very poor at taking up zinc, and high N and high vigor are also confounding factors. And again, freedom tends to confer those things on its science, so that just further compounds problems with zinc deficiency. What you see is poor fruit set and kind of a hens and chickens, stunted shoots, and small asymmetrical leaves. Here you can see the effect on fruit size and fruit sets. And those are the leaf symptoms. Okay, I want to talk briefly about boron before we run out of time here. Boron is an unusual micronutrient because it's kind of a narrow range between deficiency and excess. The symptoms that you would see in fruit, you get these pumpkin-shaped berries and poor set. And you also get swollen internodes and short internodes. And it's most common to get excess on the west side of the San Joaquin Valley, or in the Paso Robles areas, or some other coastal areas like Mark was talking about. Whereas on the east side, where I'm located, you tend to have deficiency symptoms. Boron deficiency in the early season is typically drought induced from dry soils the previous fall and winter. If you see deficiency symptoms in spring and summer, it's usually due to an authentic deficiency. Okay, here are some boron application guidelines. They'll be stored in the recording. Here is, I just wanted to show this before I ended, the seasonal uptake of boron in leaves, stems, and fruit again in 2 different grape varieties. And Mark pointed out in his talk how boron can start off looking fine in the spring, if you're in an area where toxicity is a concern, but by the middle to the end of the season, you start really seeing those toxicity effects. And that's because boron continues to accumulate in leaves throughout most of the season. And so it just keeps accumulating boron, and you do get into that toxicity problem in some soils. Okay, I wanted to acknowledge before I leave Pete Christensen, Larry Williams, Steve Vasquez, California Table Grape Commission, and the USDA Specialty Crops Research Initiative, which has helped us develop a lot of these data that I showed. So thank you.
Thank you, Matt. Does anyone have any questions? I don't see any currently in the chat or in the Q&A, so I just thought I'd see if anyone's going to put anything in there. It's not looking like you have questions today, Matt. It's your lucky day.
Okay, great. Thank you. Bye.
Thank you, Matt. All right, our next and final presenter is Luis Diaz-Garcia. He's an assistant professor in the Department of Viticulture and Enology at UC Davis. And he's going to talk about foundations for a modern grape breeding program. Good to see you, Luis.
Hi, Karen. Good to see you too. Is it working?
Yes, it looks very small.
Let me do something quickly. I think I know why. Working better?
Perfect. Much better.
Good. Should I start now or?
Yep.
Perfect.
Floor is
Okay,
yours.
well, thank you so much,
Thank you.
everyone, thanks so much, everyone, for being here today. I'm going to talk about some of the work we are doing in terms of breeding here at UC Davis. And I'm going to want to take a few minutes just to talk about the contributions of previous breeders here in the department, and I am talking specifically about Dr. Olmo and Dr. Walker, because breeding is quite unique. Any work that I might be doing, it's built upon previous work, and basically I'm just taking these populations and all these germoplasm and advanced selections that previous breeders develop in the program. And Dr. Olmo and Dr. Walker made a significant amount of contributions. I'm just going to give a couple of examples. Dr. Walker released these roostocks. I'm sure you know them, the GRN series. So these are roostocks that are highly resistant to a wide range of nematodes, root knot nematode and dagger and many others. Even when these when these nematodes are found combined in the same soil. So another interesting thing about these roostocks is that they involve many different species, and species that are outside the range of species that we are used to, like Vitis ripari and Rupes berlandieri. So in these roostocks, we have Vitis champignii, Vitis rofutumentosa that have very specific characteristics and the adaptative traits that makes them tolerant to nematodes in this case. And then we have these species disease resistant varieties that were recently released by Dr. Walker. So these are 5 highly resistant materials to Pierce's disease, 3 reds and 2 whites. And they are indistinguishable from pure vinifera cultivars in terms of quality, fruit quality, wine quality, and also in the appearance of the vine. So when you see these plants in the vineyard, they look like any other vinifera, pure vinifera material. Technically, these are still considered hybrids because they involve Vitis arizonica, which is the donor of the Pierce's disease resistant gene. And I think Vitis rupestris as well, but the portion of the genome that is coming from these wild species is pretty low. So I have these pie plots here. So you see the composition in terms of the different varieties that are found on these different cultivars. And just the green part of the pie plot is the wild species. And as you can see, it's pretty low. And what does that mean is that quality-wise, these plants are pretty good, and again, compatible with any other vinifera material you can think of. So what's coming next? So we are working now on developing materials that have Pierce's disease resistance, but also powdery mildew resistance. They're going to have pretty high percentage of vinifera, so again, in terms of quality, you won't notice any difference with any of the traditional pure vinifera materials. They still want to have the PDR1 allele, which is the one that confers full resistance to Pierce's disease. And they are going to have multiple genes associated with powdery mildew resistance, and this is to produce durable, strong protection against this pathogen. And the idea is to have a variety of materials, things that have early ripening, late ripening, different productivity levels, high vigor, low vigor, things that we can use for varietal wines or for blends, tenturiers for color correction and things like that, and also different wine profile characteristics. So these are things that have been, we're working with this. You should expect to see some releases in the next few years. So, I mean, these contributions have been incredible for viticulture. So these are, roostocks that are highly tolerant to nematodes, new wine grade materials that are resistant to Pierce's disease. The situation with these efforts is that it took so long they take so long to develop. So we are talking about 20, 30 years to develop a new cultivar. And this applies also to materials that have been developed in other breeding programs outside the US or in the US. It's just a very long process in general. And this is even considering that, for example, for species disease resistance, the trait is controlled by just one gene. And these genes are easy to work with. Again, it's just one gene that is required to have full resistance to species disease, and the same apply for other specific diseases like powdery mildew. So the problem is, as we probably have seen in the news and everywhere, climate change is going to change the conditions and the ways we grow grapes. And so we're moving into a different space of characteristics or traits that are going to be needed on these vineyards of the future. And I'm talking about things like drought tolerance and improve fruit quality and increase yield and resistance to a variety of different diseases. So many of these characteristics are controlled by many genes. So these are known as polygenic traits, which is a little bit more complex to work with. So the way we have to, approach the problem on in terms of improving these characteristics is going to be different. And there are there are many problems associated with improving these characteristics, but I'm going to talk about what I think is more important. So one of the problems is just field space is limited. So if you think about a specific space in the field, maybe you can accommodate, 2,000 vines in an acre of vineyard. If you're, for example, working with maize, breeding maize or any other cereals, you're gonna have 30,000 plants. So just in terms of the space and the cost associated with that space, that's a huge investment. And again, the problem with the polygenic traits is that as we increase the number of genes that we are trying to combine and integrate into new materials, the number of plants increase exponentially. So we need more and more plants. So people talk about breeding as being a numbers game. So the more plants we can evaluate, the better. But again, in the case of grapes, this is an important constraint. The other problem, and it is not only something that happens in grapes, but almost in all the fruit crops, perennial fruit crops, is that vines grow very slow. So depending on the trait we are trying to improve, we are going to need a variable number of genes, a variable number of years in order to make a decision. So for example, if we are improving, let's say, fruit color, I do a cross, I generate a bunch of seedlings, I grow the seedlings, and maybe after 2 or 3 years, I will see the color of the fruit. And maybe, if I'm selecting for stronger reds or whites or whatever my goal is, this is something I can do, relatively quickly within the breeding pipeline. And the same apply for other characteristics like muscat aroma. Maybe after the 2nd or 3rd year, I'll be able to see, the specific vine, specific genotype has a muscat aroma or any other characteristic I'm looking for. But then we move into a group of traits that are controlled by more genes, and we need more data in order to say, okay, this plant has potential, has the characteristics I'm looking for, and this is what I'm going to use to make more crosses and generate, new progenies, or this is what I'm going to release as a new cultivar. Then we have things like drought tolerance and yield, which are characteristics that are more complex, and there are more genes involved, and therefore we need more data. For example, if we are breeding for yield, we're going to have many years of information to see, how consistent yield is for the genotypes we are evaluating, and then we can make the call. So let's say we are interested in salinity tolerance. Maybe I will grow the plant for 5 years in a specific location. I will determine which plants grow better, and then I will choose 1 or 2, and those are the ones that I'm going to use as parents for the next generation. So in this is just an example, but might take, let's say, 8 to 10 years to make that call, and that's just one generation. We have to repeat the process, 5, 6, 7 times. It's a very, very long process. So you can think about breeding as this, three-dimensional space, so this space have basically the 3 most important components that we look into a breeding program. So we have 3 axes. One axis is the number of plants we can evaluate in the breeding program, the time required to evaluate those plants, and then any improvement we do on that population of plants. So initially, what we do is, we do crosses between the parents, between the plants that we consider are the best. The more we can do, the better. So we start with a high number of plants that we evaluate and what we call the preliminary trials. So in these trials, the cost per plant is very low because we are talking about plants that are not replicated. These are usually plants in the greenhouse, potted plants, 1 plant per genotype. So the cost of screening for that specific plant is pretty low. And also screening those plants is not that expensive because we focus on things that are very easy to phenotype. So which plants are stronger, which plants germinate, things that you can just see with your eye. So if you take into account the cost of doing that, it's not that high. So then we keep selecting plants. So we filter out the things that we don't like. As we move forward into the breeding pipeline, we start looking into traits that are more important, but also more difficult to measure and more expensive. So by the time we go to the elite trials, we are maybe working with 5 to 10 different genotypes that we can plant on different locations. It's many plants per genotype, and it can be an entire row in a vineyard planted with the same genotype, so we can have more reliable information about how good these genotypes are, and then we can just decide which genotype is the best, and we can release it as a new cultivar, or we can just use it as a parent and for the next generation of breeding. So this is more or less how traditional breeding looks like, and what we are trying to do is to increase the number of plants we input into the breeding pipeline. And you can think about this as lottery tickets. So if you buy more tickets for the lottery, more chances you have of winning the big prize. But again, there's a cost associated with that increase in the number of plants we are evaluating. The thing is that having more plants allows us to increase the population means of how these plants are performing, because we have more things to look at. And potentially that has implications in terms of the genetic performance of these plants. And also what we are trying to do is to evaluate these plants faster, so we can reduce the time required to identify a potential new cultivar or a potential new parent, but also we are increasing the population mean. We are not really skipping phases of the breeding program. So we still have to evaluate these plants on elite trials, multiple locations, highly replicated experiments, but probably reducing the time for each of these different stages. So basically, these are the 2 goals we are pursuing in my program right now. Increasing the number of plants in the breeding program, the plants that we introduce into the breeding pipeline, and also how quickly can we screen those plants. And I will give you a couple of examples, a couple of traits for which we are developing methods that allow us to do exactly that, reduce the time and increase the number of plants we can phenotype. So one of these traits we are focused on is salinity tolerance, and particularly chloride. We all know that this is a huge problem in many viticultural regions, including California. There is a high cost involved in salinity. Salinity has impacts for the structure of the soil, can affect water uptake. When these plants grow in high salinity, so salinity can accumulate in the plant, in the fruit, and this affects fruit quality, wine quality as well. So it's an important problem. But the good thing is that there are very good sources of salinity tolerance, and that's the most important thing for a breeding program. If a breeding program doesn't have the sources of variation, the sources of resistance, there's nothing to do. But in this case, thanks to the efforts of going back again to Dr. Ullman, Dr. Walker, that collected germplasm, all over the world, the southwestern part of the U.S. and other regions. Now we have this collection of plants in the vineyard that have very unique characteristics. And in this case, we have identified a few accessions that grow pretty well under high salinity conditions. So these are potted plants, different genotypes, and these plants were grown under high salinity conditions. So we were watering these plants with 75 millimolar sodium chloride for a couple of months. The same conditions, side by side, and you can clearly see the difference. So the first two, it's a particular genotype. You see the wilting, you see some salt crystals in a few leaves. But then we have this other accession. The species is Vitis zoaniana that is growing perfectly well. So somehow this plant, keeps the ions, chloride ions, outside the root system, and this is how it's growing well. So we have been doing several trials with different accessions. So basically, we grow these plants on pots. We irrigate them with high salinity water for a few weeks, and then just collect the leaves and measure the amount of chloride on these leaves. And based on that, we determine which plant is chloride excluder, which means tolerant to chloride, and which plants are chloride non-excluder or susceptible to this particular condition. And in this graph, in the x-axis, we have different genotypes, different accessions. You see a couple of commercial rootstocks, 140RU and Ramsey, that are known to grow well under high salinity conditions. And then in the y-axis, we have the amount of chloride in the leaves. And different colors of these bars are different concentrations of salt, different treatments that we apply to these plants. So 140RU does pretty well in terms of the amount of chloride that is absorbed, so it's keeping most of the chloride outside. But we have some accessions that perform better, like Vitis zoaniana, the one that I showed you in the previous slide. We have Vitis longii, Vitis giridiana, that perform better, which means these plants are excluding, it's keeping the chloride outside. So the problem with this is it's a very time-consuming process. So to characterize these plants, we have to propagate them in the greenhouse. We transplant them to these 4-inch pots or other types of pots, and then we grow them for a couple of months. We irrigate them. We apply salt with water. And then we have to take the leaves and grind them, and then we use this machine to measure the amount of chloride on the leaves, and that's how we determine if a plant is chloride excluder or not. So again, if you remember, one of the goals was to increase the number of plants we can measure. Well, with this methodology, it's pretty difficult. We can probably do 300 to 500 per year if we want to do it right. So we have been looking for alternatives that allow us to increase the number of plants we can screen. And we're interested on these machines that are called spectrometers. And the idea is pretty simple. So spectrometers can basically measure reflectance in a very wide range of the spectrum of light. Visible light is just a small portion of the light spectrum, 400 to 750, 800 nanometers. But there are machines that can go beyond that, so 2500 nanometers or even more. So near infrared and infrared, all those different ranges. And this technology is very powerful because, for example, when we grow a plant under no stress, so good conditions, light that is reflected on these plants have a very specific spectral profile. But when we grow the plant under stress, the stress, whatever the stress is produces changes in the internal structure of the plant. Different biochemical components, maybe the photosynthetic machinery and other characteristics inside the leaves, and those changes affect the way the light is reflected. And what we do is basically compare or look at the differences between the perspective profiles that plants under stress produce with the plants that grow under normal conditions. And we use those differences to predict stress responses. So we have been doing experiments in which we grow these different plants under stress. We get spectral measurements with this machine, which is very simple. It's just going with the machine, pinching a leaf is a non-destructive method. It takes like 5 seconds per measurement. And then at the end of the experiment, we still collect all the leaves. We calculate the chloride concentration with the traditional method. But then we combine the spectral information with the chloride concentration into prediction models. And then we use those models to predict what's going to be the chloride concentration on new trials, on new plants. So we repeat, and we do another experiment with entirely new set of plants. We don't have to do the chloride quantification with the traditional method anymore. We can just use the spectral machine, get the measurements from each plant, put that data into the model, and the model is going to predict if the plant's going to be, for example, excluder or a non-excluder. And again, this is a non-destructive method and takes a very short time, 5 to 10 seconds. And what we have seen so far is that the prediction accuracy is pretty high. So right now we're in around 0.9, which is pretty decent. So, we can now maybe do, 5,000 plants, 10,000 plants per year using this methodology. The other trait we are interested in is growth rate, and we are still trying to figure out how growth rate at this stage, small plants translate to field conditions. But I want to show you a couple of very cool videos of the data we are recording in regards to this specific trait. So we have a robot in the greenhouse. It's very simple. It's a big space. We can accommodate between 1,000 and 3,000 plants, depending on the size of the plant, the size of the pot. And then there is, in the end here, you can see there's an arm that moves along this space. And this arm has different cameras that point into different directions, so we can have photos from the same plant from different angles. It has an hyperspectral camera, so we can have more information about the physiological status of a plant. We can calculate things like NDVI, that is very informative when a plant is growing under stress conditions. And then we use machine learning to find all the plants, and depending on the size of the plant, we can supply different amounts of water. So we can take into account, growth rate and provide water depending on how big is a plant. So then we can generate this type of video. So this is a plant growing. This is probably like 6 weeks of growth, and so we can have these like time-lapse videos. We take all the pixels that correspond to the plant and calculate what's going to be the biomass. And we use machine learning also to, for example, estimate plant height from a single photo, which is quite trivial if you think about it. A human can, easily determine that plants growing is getting taller, but for a computer, it's not that easy. So we use machine learning to calculate what's going to be the height of the plant using just these images. And here in this video, the wider it is, the taller the plant is. So we combine all that information to calculate growth rate, how the plant is developing. And then we compare on the different stresses how these plants are performing. So this is another example. These are a couple of different genotypes growing under stress. You can see one of the plants growing way faster than the other one. Again, these are exactly the same conditions, just two different genotypes. And then the final trait we are interested in is root architecture. So there is research that has linked root architecture with drought tolerance. So root systems that produce longer roots have the capability to explore more soil space, and in some cases these are considered drought tolerant plants, compared with root systems that are more superficial, closer to the surface, more fibrous roots like 10114, which is considered drought susceptible rootstock. So the problem with the measuring roots is that it's very difficult to measure them because they are, under the soil. So if we want to look at one or two plants, we can just dig a hole and look at the plant, and I mean it's simple. But if, in a breeding program, we are interested in measuring thousands of plants. This is extremely complicated. So what we have been doing is building these rhizotomes, which are very simple boxes. They're like 16-inch by 14 inches, and then the thickness is probably like 1.5 inches. The back of the rhizotome is black, and then there is one face that is transparent, and we place these rhizotomes 45 degrees with the transparent side looking down, so the roots are always exposed to the transparent side of the rootstock of the rhizotome. Sorry, and we basically we're able to see the roots with this specific system, and we have seen very interesting patterns. So this is a couple of photos which took last week from Guantanara and 10114, and you can clearly see the differences between the two rootstocks. Guantanara, going deeper with thicker roots, and then we have 10114 more fibrous root system. So we have a mapping population, which means just a cross between Guantanara and 10114. We have about 120 individuals, and they segregate for root architecture. So there is variation in how the roots look like. And the expectation is that these differences correlate with different characteristics in terms of drought tolerance. And the goal for this type of work is to develop machine learning models and computer vision platforms that are able to measure root architectural traits, correlate these characteristics with gas exchange parameters like stomatal conductance, photosynthesis rate, that are very good indicators of drought tolerance, and also identify genes that might be involved on determining root architecture, so we can accelerate breeding. So these are just 3 examples of things that we are trying to improve in terms of the efficiency in which plants are screened, and again, with the goal of increasing our capabilities in terms of the plants that can be screened overall in the breeding program. So this is all I have. This is some photos of the people that are actually doing the work in the lab and in the field, and again, the organizations that have contributed with funding. So that's all I have. I don't know if you have any questions, or I don't know if we have time.
Thank you, Luis. I'm looking to see if there are any questions in the chat or the Q&A, and I'm not seeing any at the moment. But maybe as I'm talking and thanking people, there might be a couple that crop up. So hang in there 1 second. Thank you, first of all, Luis, for talking today. Really appreciate it. I'd also like to again thank Mark Battany for discussing relevant topics for today, and for Caroline Bamforth for helping with logistics. Of course, all of the other speakers, as well as Luis, and including Luis, for their willingness to share their time and expertise here today. And of course, our extension partners, as I mentioned before, without them, we wouldn't be able to do all the presentations and work that we do out to the industry. And thank you all for attending today's program. And I do see I see something in the Q&A. In the chloride excluding vines, did you see a decrease in nutrient uptake?
We haven't. That's one of the limitations of the platform. That we are measuring very small plants, and the expectations is that these characteristics translate to the field once these plants are grafted and growing on the real conditions. So what we are going to do next with this kind of expensive is to do nutrient analysis on leaves on all these different plants to see if there is other effects on other nutrients. But I don't see any deficiencies or any other affectations on the plants like the ones that I was showing to Aniana and the other tolerant plants. We are also developing a similar methodology, but for boron. So exactly the same idea. We are stressing the plants with boron, measuring them with the spectrometer, and then quantifying the concentration of boron at the end, and then it's exactly the same idea, developing the same prediction model. But yeah, probably we need to do tissue analysis for other nutrients. It's just it's kind of expensive. We're gonna do like 500 plants or 1,000 plants to develop accurate prediction models. But yeah, that's something we should consider. Thank you.
Yeah, interesting. Up. Someone just said thank you for the presentations. So she was happy with the presentations today.
Perfect.
Great. Thank you all very much. Have a wonderful rest of your Friday and have a great weekend.